Hello, so we're group 11 and we'll be presenting our EM theory project on plasmonics. So starting with what is plasmonics? Plasmonics is a field of physics which lies at the intersection of photonics and nanotechnology. So plasmonics basically involves the creation, study and manipulation of signals embedded in optical frequency oscillations of surface electrons along metal dielectric interfaces. So in plasmonics, basically, the optical frequencies are confined in sub-wavelength scales, and this provides an interface optical electromagnetic field and nanoscopic device. This provides an interface for optical electromagnetic fields and nanoscopic devices. These interactions lead to charge oscillations, which are called plasmons, and these plasmons are excited when the external electromagnetic field matches the frequency of the resonance, matches the resonance frequency of the nanometal or the nanoparticle. So the electron is free and it's free to move within the boundary of the particle surface, but it cannot escape the surface, and this is why that this effect is also called localized surface plasmon or plasmonic resonance. This finds applications in fields such as nanophysics, nanochemistry and nanobiology, thus making it a very important field. While the quantum mechanical nature of nanoparticles makes their properties, especially their optical properties, hard to understand, luckily for us, the plasmonic effects can mostly be understood in a classical framework, and we will begin with the historical perspective on this matter. Then we will need a framework to describe three distinct features: the metallic characteristic, the size and the shape of the particle. We will start with the Drude model, then look at a quasi-static approximation, which will let us take into account the nanoscale size of the particle, and then we will use the generalization of the Clausius-Mossati relations, and this will let us consider a particle embedded in a dielectric medium and the effect of its shape. And finally, we will combine these to build a classical model for the plasmonic resonance in metal nanoparticles. Now coming to a brief history of plasmonics. Although nanotechnology as a field didn't emerge until a few decades ago, the ancient Greeks and Romans had been using nanotechnology without labeling it. So, for example, if you look at this image, we have a chalice wherein when light is reflected off the glass of the chalice, it appears to be green in color, whereas when light is transmitted through the glass, it appears to be a ruby red in color. This is an interesting phenomenon that actually involves these amazing effects of plasmonics. So the first person to actually perform scientific experiments on the optical properties of nanoparticles was Michael Faraday, and he focused on gold colloids. After him, a satisfying classical explanation was given by Maxwell Garnett, who combined the new Drude theory of metals with Lord Raleigh's description of electromagnetic properties of small spheres. Then Richard Gans extended the description of optical phenomena to oblate and prolate spheroids. But however, all of these properties were based on the optical properties of bulk metals. And finally, in 1970, we finally took the nanoscale size into account, and it became clear that size, shape, arrangement, medium, and temperature all have a crucial role in controlling the intensity and frequency of plasmonic resonances. So let us start by examining the object under the study, the metal nanoparticle, and its defining features. We will begin with the classical derivation of plasmonic resonances, starting with the Drude model for metals. So we know that the electric displacement D is equal to epsilon naught E plus P, which is the polarization, which is epsilon naught epsilon E. Using the Lorentz oscillator model, which assumes that the electron undergoes damped oscillations under forcing, where the force is provided by the electric field, we come up with the classical damping equation, which is the classical damped oscillator equation, which is mx double dot plus m gamma x dot plus m omega naught square x is equal to E et. Now we use the Matthiesian's rule, which says that the total damping constant gamma is basically a summation of all of the inverse time constants of each component. So gamma is equal to summation j 1 by tau j. Now we take E of t as E naught e to the power I omega t, and so x of t also becomes x naught e to the power I omega t. So if we look here, plugging x of t back into the original equation, we get mx double dot, which is minus m omega square x naught e to the power I omega t, plus gamma x dot, which is plus I gamma m omega x naught e to the power I omega t, plus m omega naught x square, which is just m omega naught x m omega naught square x naught e to the power I omega t is equal to e naught e to the power I omega t. Getting rid of the exponential terms, we finally get x naught is equal to e naught by m 1 by omega naught square minus omega square plus I gamma omega. Now we see that the dipole moment can be calculated from this. P of t is equal to e to the power is minus ex by t, x of t, which is equal to minus e square e of t m omega naught square minus omega square plus I gamma omega. And we see that the polarization, the dipole moment density, which is equal to the dipole moment per unit volume, becomes minus n p of t, which is equal to n e square by m 1 by omega naught square minus omega square plus I gamma omega e of t. Finally, using the fact that d is equal to epsilon naught e plus p, we get e, the relative dielectric constant, as 1 plus n e square by epsilon naught n 1 by omega naught square minus omega square plus I gamma omega. This can be further decomposed into its real and imaginary parts as shown here. And then in the 2-day model, we assume that the electrons are free, and so they do not experience any force from the nucleus. This means that omega naught becomes 0, and so epsilon m in the medium becomes 1 plus n e square by epsilon naught m 1 by minus omega square plus I gamma omega. This can be further written as 1 minus omega p square by omega square minus I gamma omega, where omega p is nothing but n e square by epsilon naught m, and is also known as the plasma frequency. This can again further be split into its real and imaginary components. Finally, to account for the positive background of ions in the constant term, we get epsilon m infinity, which is just minus omega p square by omega square plus gamma square minus I omega p square gamma by omega cube plus omega square plus gamma square omega. Now, coming to the quasi-static approximation. To find the polarization of the metal nanoparticle by the electric field, first what we do is take into account that it's a nanoparticle, which means that the size of the particle is much less than the wavelength of the electromagnetic field. And so we can assume that the electric field is experienced, basically the spatial component of the electric field is the same throughout the particle. Basically, E naught RT, which is E naught e to the power I omega t minus kr, can just be approximated as E naught e to the power I omega t. With the electric field not depending on R, the polarization now becomes uniform, and the effect of the quasi-static approximation on the total dipole moment is very conveniently translated to P NP equals Vp, where P NP is basically the dipole moment of the nanoparticle, V is the volume of the nanoparticle, and P is the polarization density. So the quasi-static approximation lets us drop the dependence on the position R, and in this treatment we assume that the skin depth, that is the distance the field has to penetrate the metal for its amplitude to decrease by a factor of 1 by E, is larger than the size of the nanoparticle, hence allowing us to assume that the field can penetrate the nanoparticle completely and the uniformity of the polarization can still be assumed.
We now move on to find the polarizability of the nanoparticle. And in finding that and doing all the math, we come across to relations called the Clausius-Mossotti relation. This basically relates the microscopic properties of polarizations of individual nanoparticles, and the macroscopic bulk properties like the dielectric constant of a material. So those are the Clausius-Mossotti relations, and we're going to get there. Can you go up? Yeah, so we start off with the general size of the nanoparticle. We assume that it's an ellipsoid and not a circle, not a sphere. So this ellipsoid has a dielectric constant of epsilon m, while the surrounding medium has a dielectric constant of epsilon h. H stands for host. It has semi-axes ax, ay, az to characterize its ellipsoid shape. We now need to find the polarization of the particular nanoparticle, and we know that the polarization is basically this, where alpha stands for the polarizability tensor. We need to find alpha so that we can find the Clausius-Mosotty relations. If we assume that the dielectric medium is linear, homogeneous and isotropic, then the local field is proportional to the applied electric field. If it is not, then it's a complicated relation, but here we assume that it's linear, homogeneous and isotropic. The total electric field will depend upon the external electric field and also the polarization caused because of movements of charges inside the particle. So, can you go down? More. Yeah. So, with an applied electric field to the medium, the particle in of itself will be polarized. While we know that this is metal nanoparticle, while we know that metal nanoparticles, the potential is zero and there's no charge distribution, but you have to understand that the size of this particle is of the orders of the skin depth of the electric field. So that means that you are going to have varied electric field here and inside the particle at a different point, and hence you are going to have charge separation. So this charge separation is obviously going to be opposite to the applied electric field, external field, and this is in fact going to lead to more polarization in the host medium, because that itself is also a dielectric. So you're going to have both polarization inside the medium and polarization outside of the host. If we take this Gaussian pillbox at the surface of the nanoparticle with the host interface, what we can do is, if we take this as a pillbox, we know that the surface integral of E dot dA is going to be Q by epsilon naught. And if we assume that both of these are parallel, which they are in our pillbox case, you get E as Q by epsilon naught, which is just if you multiply D on both sides, this becomes the volume of a small pillbox and with area A, and that is just P by E, where P is the dipole moment divided by volume. So it's the dipole density to be fair. So if we take a Gaussian pillbox as given in the diagram above, only the depolarizing field, which is the field inside a nanoparticle, will contribute to the integral as flux due to the external field is zero. This is obvious. So the E polarization will be minus P by epsilon naught, and the E net will be the external electric field as well as the polarization field inside our nanoparticle, which is P by epsilon naught. Okay. In this case, the nanoparticle is embedded in another medium, where induced charges in the nanoparticle will lead to more induced charge in the medium at the interface, which leads to reduction in polarization. We, after finding this term, this extra polarization in the medium, get the electric field, the local electric field as Ej naught, which is the external electric field, minus Lj Pj by epsilon naught epsilon h. So epsilon h comes because you have a host media, and Lj is something called a depolarizing factor. This is due to the fact that the nanoparticle is not a small point, it's actually a three-dimensional object and it's an ellipsoid. So electric field at each point will not be the same. So after some calculations, you get an additional factor here, which is known as a depolarizing factor. It looks something like this, and if you calculate it for a sphere, it is Lj is equal to 1 by 3. You can find this by symmetry arguments, which we'll come to later. Pj, then the net polarization becomes Pmj minus Phj, and this you get as epsilon naught, epsilon m minus epsilon h into E local j. So if we combine this equation as well as the equation which we got for the local electric field, what you get is this relation. This relation is Pj here and Pj here. So if you solve for Pj, you get something like this. Now we know Pj, and we also know from Druday's model that we can find P of Np to be Vp. So this is already written here, I don't know why I wrote it. But so that is Pnp, which is Vp. So if we just use that, which comes from the quasi-static approximation, you get Pnpj as something like this. This is the microscopic polarization of each nanoparticle. This implies from this relation, which we already know, that Pnp is basically epsilon naught epsilon h into the polarizability tensor and into the external applied electric field, you get alpha j as something like this. We can now actually see that alpha j is a diagonal matrix because you only have j terms, which means that if the incoming electric field is along one of the axes of the ellipsoid, the polarization is parallel to it. Note that because this is a matrix, this makes the system anisotropic because the response of the system in x, y, z is not going to be the same. You can clearly see it's different as it depends on Lj. So calculating Lj, if you remember, Lj was a complex integral, right? Calculating it is actually a laborious task, but you also have a relation which states that the summation of Lj over all directions is just 1. You can prove this simply. It just depends on the symmetry of Lj. And using such a normalization property, finding values for Lj for objects with symmetries or objects with one dimension being too large can be a trivial task. Here are some values for a sphere, long cylinder and disk. For a sphere, you can use symmetry arguments which says that Lx has to be Ly has to be Lz, and hence that should give you Lx equal to Ly equal to Lz is equal to 1 by 3. Can you scroll down? So now with Lj, now with Lj being 1 by 3 for spherical particles, we can finally write the Clausius-Moussorti relation. Remember, you had an expression for alpha j on top, you substitute Lj as 1 by 3, and this is what you get. And this is what I was talking about. You're relating the microscopic property of the system, which is alpha j, from which you can get PNP, which is the microscopic polarization, with the macroscopic property of the material's dielectric constant. We now move on to plasmon resonance, which is a characteristic of this. So from Drude's theory, we know that for a metal, you can find the dielectric of the metal as this, okay? From our calculation of the polarizability matrix, we also know this. This is a relation which we just proved, right? We can plug this here, and then if we assume that you have gold-like Drude particles, which means that I just choose some values of these constants, we can find a relation between the modulus of the polarizability tensor and the wavelength. We coded it out and we get a graph of something like this. This graph is sharply peaked at some characteristic wavelengths, and this depends upon the surrounding host. So if you go down, this is a sharp peak, and as I said, there is a resonance frequency because at some point alpha j is large. Notice if alpha j is large, that also means PNP is large, and if polarization is large, that also means that the dipole moment of each nanoparticle is large. That means that what you have is a sort of a resonance frequency where the amplitude of oscillations is going to be highest at this peak because you're going to have the highest dipole moment, and that means the amplitude is going to be highest. You can make an approximation from this. Can you go up? You can make an approximation. Go up, please. So if you use this, you can say that for this to be maximum, the denominator has to approach 0. So if you do that, what you actually get is you get the imaginary part of the dielectric constant of the material to be 0, while the real part to be this. You can clearly see that this real part depends on both the host dielectric media as well as the shape of the particle. Note, however, there's no dependence on the size of the particle, and that is one of the shortcomings of what we're doing here. We can find omega resonance by basically plugging in these values into the Drude equation, and you can find omega resonance which equals omega p divided by root of this quantity. These equations clearly show that the resonance frequency depends on the geometrical features of the nanoparticle and the dielectric medium in which it is immersed. The dependence of these resonance shift due to changes in epsilon h enables a multitude of sensing applications. So if this changes, you're going to have different peaks, which allows us to find what the surrounding media is. For the special case of spherical particles, you get the resonance frequency of the nanoparticle to be omega p by root epsilon m infinity plus 2 epsilon h. We're going to use this relation in the future. Note that for this resonance to exist, this has to be 0, which basically means that damping is going to die out. Okay? This is to keep damping at a minimum, and for this reasons, the most significant plasmonic materials are also the most conductive, which have the least damping. One promising aspect of plasmonic resonance is that outside our nanoparticle, we can assume the buildup of electric. So we can assume a buildup of an electric dipole inside the particle, and you can get the local field outside the nanoparticle to be the applied electric field from outside plus the electric field due to the dipole. If you think about it, resonances will reflect on PNP and subsequently on ER. This means that you're going to get an enhanced local electric field at the plasmonic resonance. This enhancement due to plasmonic resonance can make the local electric field tens or hundreds of times greater than the incoming field. The shape can be changed to basically have a different resonance frequency and hence a different build-up of a different electric field component. If you move down, here are some FTTD or finite time domain simulations in which you have an electric field coming into the XY plane and you're measuring electric field in both YZ and in XY, okay? And you can clearly see there's a build up here. These diagrams shows these simulations for a spherical gold nanoparticle in water with an applied electric field of 540 nanometers. The finite time domain simulations solve Maxwell's equations in discretized space and time, characterizing each portion of space with the complex dielectric function and as well as magnetic permeability, because the Maxwell's equations also mean you solve the magnetic field. These simulations introduce minimal approximations and are hence like the gold standard, they're accurate. Using this simulation, the plasmonic resonance occurs as 540 nanometers as compared to our predicted 520 nanometers, so our theory is sort of off track from the actual value. This shift is mainly explained due to radiation damping, which shows that the QSA approximation does not always provide accurate answers. We are going to talk about this in the next presentation.
Okay, now we go a little bit beyond the quasi-static approximation. So quasi-static approximation works really well to describe effects such as absorption of certain colors or the local field enhancement in the proximity of metal nanoparticles. However, it fails to predict other effects which are related to the size of the particle, as size is irrelevant as long as it is smaller than the incoming wavelength. The first correction. Okay. Now, earlier when calculating the damping factor gamma, we only took in collisions of electrons with other electrons, nuclei and phonons. But the electrons also collide at the surface boundary of the nanoparticle, which are also very relevant. So we say that let the electrons move with the Fermi velocity Vf, and the time between two collisions within the boundary is tau boundary, and tau boundary is thus defined as lambda boundary by Vf, and lambda boundary is the distance travelled between successive collisions. And as we know from Matthiesen's rule, gamma is just a summation of inverse of tau constants from all the collision modes. So gamma is equal to gamma bulk, which is our earlier gamma factor, plus 1 by tau boundary, which we added to account for the boundary collisions, which is equal to V Fermi by lambda mean free path. This is the usual gamma, plus V Fermi upon lambda boundary. So we now need to calculate lambda boundary. So as we can see, we take a spherical nanoparticle and it is pure, so x square plus y square plus z square is equal to r square. So assume this is a nanoparticle. Without loss of generality, we can say that an electron collides here and then moves like this to a random point on the sphere x prime, y prime, z prime. So this point could be anywhere. All points have equal probability of getting collided with. So we define this distance as dO prime, which is equal to x prime square plus y prime square plus z prime minus r whole square. And simplifying this, we get root 2r under root 1 minus z prime by r. Now, to calculate lambda boundary, because this is basically the lambda boundary, which is the distance between two successive collisions, we need to take average of this value. So basically, to take average, we do this and we take an integral with at z prime is variable and theta is variable. We take this integral and this simplifies to this. This is 1 by root 2 minus r to r and root 1 minus z prime by dz prime. And we use the substitution 1 minus z prime bar is equal to a, and we get lambda boundary to be 4r by 3, which is So as we can see, lambda bound is 4r by 3. So as we derived earlier, our epsilon n is this, which we derived earlier, and if omega is very greater than gamma, which is usually the case, we can ignore the real part. We can ignore this gamma square, so it will just become epsilon n infinity minus omega p square by omega square, and the imaginary part will just become omega p square gamma by omega p. So as we can see that the real part doesn't contain any gamma factor, which we changed earlier. So the real part would change due to the surface collision effect. Only the imaginary part will change. So putting the newly calculated value of gamma in this equation of the imaginary part of the permittivity, we get epsilon 2 is equal to epsilon 2 bulk plus a constant times Vf by R. So as we can see that epsilon 2 is inversely proportional to R. So the smaller the nanoparticle is, the larger the imaginary part of the dielectric constant will be. Which is very concerning, because when we took our earlier assumption for resonance, we took that the imaginary part of the dielectric constant is very negligible to get a resonance. So due to this effect, smaller nanoparticles will have a diminished peak at resonance, and they will have a wider full width half maxima. So they will be more spread out, as the imaginary part is also responsible for the full width half maxima of the resonance peak. And we have also coded out the alpha, which is the polarizability per unit volume with the wavelength for various radiuses. So as we can see, for a larger radius, the imaginary part is not that high, so we get a higher resonance peak. But for as we lower the radius from 40, 20, 10, 5, we get lower peaks, and the full width half maxima widens, which we derived earlier. Thank you.
So earlier we had considered resonance due to dipolar approximation, that is valid as long as the size of nanoparticle is much smaller than the wavelength of incident light. So basically that is when d upon lambda is much less than 1. So in that case, all we do is will also be much less than 1. So we roughly set k dot r to be equal to 0. But in this case, we'll consider the effect of finite size of nanoparticles, due to which k dot r won't be exactly 0. So if that is the case, one way of doing it is to use computational methods, but the equations are too long and that will be computationally expensive. So instead of doing that, we'll consider another approximation. We'll consider a Taylor expansion up to third order. This will give us an analytical result, while at the same time will give us the idea of this MLWA. So since the incoming light has an oscillating electric field, so that will be something like a sinusoidal form, e to the power iota k dot r minus omega t. So our dipole moment will also be of similar form, and so it will undergo harmonic motion, and p double dot is minus omega square p. So basically the dipole is like, I have an atom, I have a nucleus and an electron. So under the external electric field, the charge can polarize and it will basically form a dipole. And the electric field due to this dipole will have a radial component and a theta component, and this will derive later after this. And due to the polarization density P, due to the incident field, the electric field in a volume dV is given by these expressions. So basically it's like, if this is your radial direction in polar coordinates, this is the theta direction. So the parallel component that is along this axis will be the cos theta part, the DER cos theta minus the theta component, the sine of theta component. Similarly,
So
this is the parallel component and the perpendicular component. So we'll now integrate the perpendicular component over the whole volume. So just substituting ER and E theta. So this is the expression for DE, and integrating over volume. So we'll get R square sine theta dr d theta d phi. So this will be 0 because sine square theta cos theta is 0. So for the parallel component, we substitute E perpendicular, E parallel. We again do the similar calculations. So we can see that the parallel component has a real part and an imaginary part, and we'll substitute omega equal to Kc. So this is the result for a spherical case. Now this can be generalized to an ellipsoid by just replacing R with the semi-axis length of that ellipsoid. So when the nanoparticle is small, so in that case we can say that d by lambda is much less than 1. So roughly k tends to 0, which is our quasi-static approximation case, and in that case it is obvious that alpha MLWA should be roughly equal to alpha j. But when we are not in the k tending to 0 domain, there are two terms. One is the real part, another is the imaginary part. So the real part is called the dynamic depolarization, and since its coefficient is real, it will correspond to the effective depolarization factor. And the imaginary part comes due to spontaneous emission of radiation, and this part is called radiative damping. So we'll plot these MLWA corrections to the quasi-static approximation for a few value of radius. So here we can see that as radius increases, first of all the height of peak decreases and the polarizability broadens.
So in the last part, where we saw how the resonance occurs, considering the modified long wave approximation, we had used a formula for the electric field due to the oscillating dipole, which comes out to be this. In this part, I'll show that how we can derive this expression using something called a pair of by defining a new pair of potential which are called Hertz vectors. So we start with a new pair of potentials which are pi e and pi m, which can be sort of thought as a relevance to the electric field and magnetic field, and we call this Hertz vectors for the polarization potentials, since as we'll see that they relate to the polarization and magnetization through the differential equation. And first we define them in terms of our normal potential, which is a vector potential and a scalar potential A and phi. So the A bar is given by 1 by c times pi e dot plus the curl of pi m, and where the scalar potential is just the divergence of pi e. And after that we simply substitute these in the equation of the expression of E, which is minus del phi minus del A by del t, which we end up with this expression for E bar, and similarly this expression for B bar, which is the curl of A. And it's easy to see that the Lorentz condition is satisfied in this case. So the del dot A, which is the del dot of this term, plus del dot of this term, which is 0. So del of curl is 0. And the del by del t, del of phi, is just negative of this. So these terms cancel out and the Lorentz condition is satisfied. Now before coming to this, we are considering our problem in the region where we have no total charges and currents. So, and here the polarization and magnetization are also considered. So instead we write the problem in terms of the free current, so that the potential in terms of the free charge becomes this. Similarly, the del square A minus 1 by C square del 2 del T A bar is equal to, it can be written in terms of the free current. And where the free charges can be written expressed in terms of the polarization and magnetization. So free charges are given by the density is given by the divergence of the polarization, whereas the free current density is given by the P bar dot plus the C times curl of M. Note that all the calculations that are being done here are done in the CGS unit, so the Gaussian units. So we can to see how we come from the expression of potential to this. We can just substitute the del dot pi e in this expression. So here I have written out the expression, and you can say that this is just the divergence of the whole equation. And similarly, we can from the wave equation of the vector potential, we can get the equation for phi m. And if we notice that these equations are exactly similar to how the potentials for the Lorentz conditions, which are something like this. And in this case, we know that the solution is given by for example, solution for the scalar potential is given by 1 by 4 pi epsilon naught times integral of the rho evaluated at the retarded time and upon r and the integral over all space. So similarly, instead of having the charge density as a source here, we now have a source as a polarization and magnetization. So bringing that analogy here, we simply write pi e and pi m in terms of p bar and m, the integrals of p bar by r and m bar by r. And the square bracket indicates that p bar and m bar are evaluated at the retarded time, where retarded time is given by t minus r by c, which is due to the finite speed of light. Now coming to the problem of dipole, we consider a polarization which is given by the dipole moment magnitude along the n hat, and so we basically have a dipole moment aligned along this direction, and we consider that it is also oscillating in the same direction. So in that case, since we don't have any magnetization, the pi m becomes 0, and the pi e simply becomes this, and since we have a delta function, it simply becomes p of t minus rc upon r, where r is given here. R is given by the distance of the dipole to the observation point. Now we can substitute this expression in the expression of E. In this case, we have pi m is equal to 0, so this term goes. As for this term, we have p bar here. We have p bar as a delta function, and when we are evaluating the electric field, this Hertz potential at some point which is not the dipole moment, the charge density is there 0 basically. So is the polarization, and so this term also goes to 0. So the electric field simply becomes the double curl of pi e. And similarly, and we expand this using this identity. The double curl is gradient of divergence of A minus the Laplacian of E. And we again substitute that del square pi e is equal to 1 by c square pi e double dot from the wave equation. And again, because at the point of interest where we are evaluating the field, the charge density of the polarization is 0. So this basically gives us that our electric field is this, and we use the expression of pi e to get the final expression of E, which is in this expression I have written it in the two components, which is one along r bar, which is the vector from dipole to the observation point, and one along n hat, which is the direction of dipole. And I want to write this. I want to write this electric field in two components. One which is along the radial direction, along the direction of observation point and the dipole moment, and the other being the perpendicular to it. So similar to how we write the electric field in the case of electrostatic dipole. So in that case, we consider our z-axis along the n hat direction. We consider the angle between n hat and r bar to be theta. So the n bar dot r becomes r cos theta, and one of the terms cancel out, and we are finally left with that er is given by this and e theta is given by this, and which is what we used earlier in the modified long wave approximation for the resonance calculation.